Kimon Michaels holds a PhD from Carnegie Mellon. He's a co-founder of PDF Solutions and has served as the vice president of products and solutions since July 2010 and has been a director since November 1995. During his tenure at PDF, Mr. Michaels contributed to the development of the integrated yield ramp business, the DFM solutions, and the characterization vehicle infrastructure. Take it away.
Thanks, Neil, and for everyone joining us today. Quick background for those who may not know. PDF Solutions is celebrating our 30th anniversary this month. We provide a big data software platform with domain knowledge that unifies data collection, control, and analytics across the semiconductor and manufacturing operations supply chain. Like our previous speaker, the one thing we believe that differentiated data, electrical characterization, which provides the necessary insights, as we just heard, to enable the effective production, test, and field use of advanced heterogeneous package devices is important. We too provide electrical characterization data, both in chip and measured in the factories. But we'll talk today in a more general sense of what's required in the industry. So we've all heard the buzzwords of Industry 4.0 and digital twins, etc. But like in other industries, semiconductor right now is adopting these smart manufacturing techniques and starting to realize more benefits that the buzzwords promise. This includes really an explosion of data from sensors, more data coming from the equipment itself, coming from chip test and embedded sensors within chip, such as provided by Produ and others. The integration of this data with semantics models to span what were historically conventional data silos is occurring and very important to leverage this breadth of data. But turning this high dimensionality data into information really requires the application of advanced analytics, new AI and ML algorithms that can uncover relationships in cause and effect models that are beyond what's possible just by human analysis. Using this information, though, is about driving improved process control. So we have fewer failures, both in production and in the field, and the rapid diagnosis to understand how to correct either the production or understand field at risk. So the result really is these new techniques are bringing significant economic improvement to semiconductor manufacturing. Well, the semiconductor supply chain, we know, continues to grow in complexity. It's the reason for this session today. Design size, test requirements are growing. Wafer manufacturing today is, over 1,000 process steps. Heterogeneous integration is requiring much more complex back-end of line assembly. To monitor and improve the yield and performance, the quality, now it requires integrating data across the supply chain. But it's not just sufficient to store all this data in a data lake. A semantic model for combining this data is required. We need to understand the spatial, the time, the hierarchical relationship across the data, such that the advanced analytics can be applied to different combinations of this data and to turn that disparate data into actionable information. We can use this data in a feed-forward mode. We can understand drift and excursion monitoring. We can feed forward to do more drill down and diagnostics at future test steps. And we can use this data in a backward mode, feedback, where we understand the causes of performance and variability. We can optimize our processes. We can optimize our test flows with the result of driving more quality and reliability from our production, but also from the use of our test resources.
Okay, Kimon, could you expound on what a semantic data model is?
Yeah, it's a good question. So a semantic data model understands the relationship between the data sets given the underlying physical, in this case, physical components that we are making. For example, having to map from a black batch of consumables in a front-end fab to which equipment over which time period it goes through. That then has the context of what lots or wafers went through that particular equipment over that time period into which chamber. Being able to map then those wafers down to the chiplets, what is their spatial relationship, such that as you track through test and back-end assembly, you now have the genealogy of this chip, that all data associated with that chip, including time delays, holds that don't show up in manufacturing flows, can be combined in your analysis. And if you look at our industry, historically, we've always had a lot of data. Semiconductor was both very early and very late to the big data revolution. We had silos that were used by specific organizations for specific purposes, equipment data used for equipment control and Gantt chart, test data used predominantly by product engineers. But combining all this data in an actionable way is something that not until the advances in cloud compute, machine learning, the integration of the systems that is really taking off in the last several years. But the other challenge to that, Neil, is a good question, is that this data needs to be sourced across different sites and even different companies. A fabless company or system company's product might never exist in a factory they actually own. That's why they're fabless. Well, one thing this requires then is a secure two-way to communicate data across these different companies. But to really leverage the data and have the biggest impact on the manufacturing of heterogeneous parts requires not just cloud compute and analysis of data aggregated from different sites, but pushing down and at each stage during the manufacturing and test process, optimizing what can be done, leveraging this chip genealogy data. Foundries and equipment, front-end equipment companies are using machine learning to try to drive advanced process control. Test operations and test capabilities expanding. For example, Advantest now provides very high compute capability at product test. Leveraging this to optimize that test for quality, coverage, et cetera, is very promising and valuable. However, that may require data about the upstream capability of the test, which is only available through the sharing of data in a secure network. One example is our Exensio platform. It leverages the power of this data integrated into a single semantic model. But the intent is for engineers to be able to combine data from multiple sources to identify these causal relationships that affect yield, performance, quality. Again, machine learning models, advanced analytics are really required to take advantage of this high dimensionality of data. It's really beyond the comprehension of humans to find the relationships that exist today and necessary given the dimensionality that we're working on. But the intent is to use these models to monitor and diagnose changes to volume production in a predictive manner versus a reactive manner, just catching problems at final test. We want to be predictive, understand upstream the relationship such that we can control it, and then feed down this information such that we can react to it through better test, through chiplet matching, through optimization of a back-end-of-line packaging process, if possible. So we really need a single source of truth for all product data. The intent is to integrate your online and offline systems. In addition to identifying problems, being reactive to seeing when chips fail at test in the field, we want to use this understanding to drive more predictive process control to avoid the problems in the future. Requires broader, faster implementation of these online actions. The semantic model and the ability to clean and align data ensures that you have results in time and not false results from poor data. Womb to tomb product traceability, not through the front end of line, but also through the back end of line assembly facilities, becoming more and more critical given the complexity of heterogeneous integration. But much like we've heard in the previous talk, driving a closed loop product lifecycle optimization is really an opportunity. By having data over the lifecycle of a chiplet, of a packaged heterogeneously integrated part, enables us to quickly identify root causes, enables us to be more proactive and predictive in determining our process control strategies. So one example of how can we use this advanced test capability and ability to combine data to have an impact. Well, one is identification of excursions faster and elimination of the root cause sooner. So in this case, we're looking at combining fab data, including the metrology, the equipment data, wafer history data, with detailed chip test data to enable the discovery of this predictive relationship, predictive models between what process controls have the highest sensitivity on that particular product's yields. Once that's identified, new process control loops or measurement points are added into the foundry to drive tighter chiplet variance. And tighter chiplet variance is hence going to drive higher final product yield, both due to parametric and functional issues. Heterogeneous integration, though, provides a traceability challenge. In front-end fabs, traceability is very straightforward. We know the lot number, the wafer number, chip position on the wafer. They're constant. They're easily tracked from process step to process step. However, in the back-of-line assembly, traceability is a greater challenge due to singulated devices and the nature of back-end line equipment. The yield loss from back-end line is due to functional or parametric issues can be quite large these days, right? In this example, AMD has stated there's a 40% cost savings from using heterogeneous integration. However, diagnosing and reducing yield loss at assembly is a challenge. And catching it at that final package test point is expensive because now we're throwing out multiple chiplets. So we want to identify the root cause quickly, and we want to apply process control and chiplet good known die or good known chiplet definitions, which eliminate many of the parametric problems up front if possible. Well, one way the industry is trying to address this is through standards. One example is SEMI E143, which enables substrate mapping. And by substrate, it could be the wafer, the tray, the strip, etc. The standard enables equipment to exchange this information with our Exensio platform or any other factory system in a standard and concise way. Chiplets have ECID in many cases, very useful for understanding which die goes in which package. However, it can only be read at test points. And when we're looking at back-end line assembly, it's really insufficient for traceability through the entire assembly process. But creating these predictive machine learning models for heterogeneous integration requires traceability not just of the chiplets, but the passives, the consumables, through the assembly process. Collecting data at each step across this key equipment can be beneficial through the use of standards such as E142, but although they're not fully deployed, other custom implementations are required to identify and manually map the movement, such as our ALPS product today. Again, though, by tying in complete manufacturing information, equipment capability and electrical data, the movement of consumables, passives, and the chiplets, we're able to build a model which enables that rapid diagnosis of yield loss and process control metrics in the back end of line to reduce variance in the back end of line process. It also helps us optimize what we do at test at the different points, be it scribe line, wafer sort, or final product test.
Kimon, do you have any kind of data relating to how many chiplets have an ECID versus don't, especially based on the size?
That's a good question. I don't have statistics on that, at least not off the top of my head. What I find is most more advanced, if you will, chips these days are implementing some sort of ECID. However, when you get to more of the small jelly bean components, it doesn't exist. A big challenge, I think, which many people overlook is it's impossible to track passives, which ECID. And in these heterogeneous packages, the impact of passives, capacitors, et cetera, can have a pretty significant impact on your overall performance and yield. And it's been a challenge that some of the leading assembly houses have been trying to address. Right. So if we're looking to optimize heterogeneous integration, right, we're going to benefit from leveraging upstream data from the front end fab, the genealogy of the chiplets. We're going to benefit from the downstream data from on-die sensors that can be collected at test and in the field. And we're going to be able to use machine learning predictive analytics to turn this data into actionable information. The goal, of course, is to improve the economics, right, through increasing yield, reducing variance, reducing field failures. But beyond the fab data, what we're finding from both fabless and foundries is leveraging richer scribe line content as well to improve the value from test budgets and solving yield loss. In addition to Watt, foundries are placing more and more content which provides statistical resolution, not into just functional issues, but many of the parametric layout dependent yield loss mechanisms. How much variability do you get as a function of layout style? Leading fabless are also starting to put more and more scribe line content into their wafers in order to understand their specific design style dependencies to front-end process variation, particularly the parametrics. And leveraging this data to optimize adaptive test flows to drive more insight into ensuring quality and yield going forward. And the result really, if you pull this all together again, is to understand how to reduce yield variation, predominantly in this case driven by parametrics. Critical systems, medical, self-driving cars, server farms are realizing that more and more field monitoring is critical, right? The data provided by those in-die sensors enables test optimization as we go through the manufacturing by leveraging that sensor data from chiplets and determining test flows and interpreting the results. But monitoring and feedback of that degradation of reliability and performance in the field is also becoming critical. But although one intent is to catch this degradation before a critical failure occurs, a key part is turning this into rapid diagnosis of the undercurrent issue. We want to fix production to eliminate the problem going forward. We want quick identification of all the products deployed to the field that are at risk. Do you have to do a recall? But to do this requires more than just the data coming from the chip or even from chip testing during production. It must be combined with the manufacturing data to understand root cause, to drive back to the suppliers where a change is required in process control or in identification of bad consumables, for example. But if we tie this all together, really we can have predictive power from this holistic data set. Product data collected to answer product engineering questions, right? Do I have enough product? Can I meet my contract obligations? Do I have enough fast parts versus low power parts? But to do this, we really need to leverage more and more machine learning, advanced analytics to identify models that enable adaptive testing during the flow, to understand how to better bin, how to more quickly identify changes required. For example, do I need to start more lots to hit my production requirements? Maximizing the trade-off between yield, quality, reliability versus manufacturing efficiency is key, but it's based on the end target for every market. And we see the fabless and the system vendors providing more feedback and more engagement with the foundries of what is required for their chips to ensure high quality, low variance production.
Hey, Kimon, for advanced CMON process nodes, is it realistic to predict production issues once you find an in-field failure, as there can be as much as 2 years delay in that process?
Once you're in the field, as you know, many consumer products have a shorter life cycle than that. And I would say, for a cell phone, doing a feedback 2 years later to mass production is probably not practical, at least for the manufacturer of that chip. In other market segments, medical, automotive, where the life cycle can be much longer, you still need to understand very quickly as what fraction of your field is at risk. And it is useful as that continuous improvement feedback. The release cycle for chips such as automotive, it can be quite long. And so as you go through your sample and your field testing, the feedback is definitely valuable in that regime as well. Okay. So when you tie it all together, it's really a combination of data, infrastructure, and advanced analytics, which provide this predictive power. But the data has to be holistic from multiple sources, right? We want to capture as much data about the wafer or chiplet movement in manufacturing. We want to leverage all sources of electrical data that are available, be it scribe line based patterns, be it wafer sort or final test, be it or in die sensor data. And do this to drive causal models to understand how we can be predictive in catching issues upstream early in manufacturing, to apply more predictive process control models to improve the variance and yield as we go forward. So one example with one of our clients, we're leveraging that upstream data and machine learning analytics enabled us to predict downstream results such that we could fully or partially skip test and be more effective in the use of our overall test budget to improve the quality and coverage of yield. So it was not driven in terms of trying to reduce their test budget, but how could they increase with the given test budget the coverage and impact on their final production. So based on upstream bin predictions, we could look and see downstream what was the probability of a die population having an issue, and put in rules about whether a test could be skipped, whether it could be partially tested, and where that saved test budget can then be applied to other die or other wafers to either get more diagnostic data for improving models or for having improved throughput. So their assessment was, in this case, $1 to $2 million saved on just one product, while having no quality impact, in fact, in improving the quality. But to do this requires not just predictive models, but a mechanism of combining the data in that feedback loop for both verification and continuous improvement to the models. So what we see in this trend to chiplets is an increased need for a semantic data model and data infrastructure that provides this single source of truth of combining data across the supply chain from multiple vendors and owners of data that enable us to monitor and optimize heterogeneously packaged devices. But if we do this, if we combine this end-to-end data, it really requires or enables a lot of predictive power to reduce our variability, to have a better definition of known good die, to enable chiplets to be selected, to be put in the package such we don't get failures from mismatch. In-die characterization sensing, really useful not just for in-field prediction of reliability using in-field data, but also to give greater insight during test points, during production. Chiplet traceability, passive traceability through the back-end align assembly process is becoming more and more critical for rapid root cause of yield loss and quality issues, and enabling the correction mechanisms going forward, improving our process control. So we see that this combination of data and optimization of tests can have a much bigger impact on ensuring we get the benefits of heterogeneous integration that are promised today. Thanks.
Thank you, Kimon. If everyone could remember to fill out the poll that Ira will be starting, we've got time for a few questions. So back to your specific example, can you speak a little bit more specifically to kind of what parameters were used to determine whether that process could be skipped or not? Is that something you can share?
Yeah, I can share it in generalities. It was a combination of metrology information and scribe line information that the machine learning model was able to determine for that specific product, what are really the layout process sensitivities, the interactions which drove a reliability problem. In these advanced processes, what you find is that we have very little process margin. So we can end up having, for example, leakage currents through low-K dielectrics that will, quote unquote, slip through parametric test, given their natures, but you can identify the relationship by using burn-in data to understand upfront what's required to eliminate it. So it was a combination of metrology and scribe line data, but the model was very specific to the product, as it typically will be.
And can you say where the savings came from in that example? Was it really just all of being able to skip those downstream tests, or were there any other savings that were applied in there?
Yeah, so it's a great question. In that particular case, this was a combination of, or a client-driven result on what was the impact on test cost. Basically, where could they save on test costs? And again, the intent was to being able to apply test the extra test time more effectively in other places. If you're driving more value from test, we find people are willing to do more test. However, if you think of the intent, the ability to have better coverage and fewer escapes due to reliability issues, et cetera, the real savings is on field failures, returns from customers, et cetera, that are very expensive.
Okay. Could you speak to kind of the life cycle or timeline for one of kind of these analytic exercises? As we spoke for earlier, there's the shortening life cycle of chips, right? Can we actually get to something that's useful in a year or in the time it takes, especially as we get to, in chiplets, we're making smaller, cheaper chips. How do you see that kind of applying there?
Yeah, that's a really good question. I think our view, and really the challenge, is we have to pull insight and decisions upstream. As you mentioned, many chips are not in production for a long time. But if we look at an advanced product, front-end production of a 7-nanometer chip may take 4 months or more. Back-end heterogeneous integration of that flow, plus all the testing, another month plus. So if you have to wait until, call it 5 to 6 months to understand the impact on final product, not to mention when it gets into the field, that's really too long to ensure quick feedback. You already have a supply chain potentially full of problematic parts or parts with very high yield. The intent as you're doing your new product bring up and leveraging, in fact, previous products and understanding of your process is to drive forward these predictive models so that you can react in the front end fab, you can react at wafer sort test, you can react during your back end of line assembly to have tighter process control to try to avoid the problems as you go. And that field feedback ideally is mostly a monitoring and verification loop, and less over time, catching problematic issues.
All right, thank you very much.
I'd like to thank all the presenters and also thank all the sponsors who made this event possible, and their generosity covered the expenses, so everybody was able to attend without charge. Our diamond sponsor is Amkor with differentiations in technology, quality, and service. Our emerald sponsors are Advantest, voted #1 in ATE by the VLSI survey in 2001, and Synopsys, silicon to software. And then our Ruby sponsor, Tech Search International. So once again, if you have an opportunity to thank the sponsors, please do so to encourage them to help support future events and bring great information like we've had over the last 3 days here at Data and Test Road to Chiplets. And with that, I will wish everybody a good rest of your day. And thank you for joining us, and look forward to seeing you at a future MEPTech event. Thank you.